Hello viewers, welcome to online course on Mathematics 3. This course is basically for undergraduate student or BTech student of engineering field. Today we are going to discuss about the special type of distribution. So there are some special type of distributions like binomial distributions, Poisson distributions, normal distributions, standard normal distributions, uniformity distributions, okay, and so on. So today we are going to discuss only the binomial distributions and some related examples we will discuss. Okay. Myself, Sanjay Bishas, Assistant Professor of Mathematics, Department of Applied Science and Humanities of Guru Nanak Institute of Technology. Here is my details of contact information. If you have facing any kind of problem regarding my online class, so you can call me or send message through my mail ID sanjay.bishas@gnit.ac.in. So before we start today's lecture, let's quickly recall in the last lecture. So in the last lecture we have discussed about the mathematical expectations, variance and standard deviations. Okay. So in this lecture we have discussed about the expectations or mean of a random variables, okay, for a continuous case as well as the discrete case. And after that we have discussed about some deductions on expectations or some formulas or the properties of the expectations, and then we have talked about the variance and the standard deviations. Okay. So after that we have discussed about the worked out examples on the expectations, variance and the standard deviations. Okay. So today we are going to discuss about the special type of distributions, and that means the binomial distributions. Okay, so this is my fifth lecture on the probability theory, and the third chapter on the probability theory as well. Is it a special type of distributions? So in that chapter there are 5 or 6 special type of distributions. So the first one is a binomial distributions, Poisson distribution, normal distribution, standard normal distributions, okay, and uniformity distributions and rectangular distribution as well. So among this, today we are going to discuss about the binomial distributions only. Okay. So in this distribution is the actually the discrete distribution, and the Poisson distribution and the binomial distributions are the discrete distribution, but normal and standard normal distributions are the continuous distribution. Okay. So here is the content of today's lecture. First of all, we introduce the introduction the special type of distributions. So after that we will talk about the binomial distributions, so definition of binomial distributions and some properties of the binomial distributions. Okay, and after that we will discuss about some theorem on the binomial distributions. So then we will we are going to study on the workout examples on the binomial distributions. Okay. So first of all, we'll start with the introduction of the binomial distributions or the special type of distributions. Okay. So a random variable is said to have the special type of distribution if its probability mass function and the probability density function get the special form. Okay. So there are 5 or 6 such type of distributions are discussed in this chapter. So among these, the 2 discrete distributions, that means binomial and Poisson distributions, are very well known and useful in every field of life. So binomial and Poisson distributions are the discrete distribution in this chapter. So, and they are very well known and useful in every field of life. And the continuous distributions like normal distributions and the standard normal distributions has also a wide range of applications in sociology, market research, or the especially in the industries. So the definition of each of the distributions is first given, and their properties and field of fitness are illustrated in this chapter. And there are so many special type of distributions, and among these the very important are binomial distributions for the discrete case, and the normal and standard normal distributions for the continuous case. So we will discuss in this chapter. So first of all, we'll start with the binomial distributions. Okay, so the definition of the binomial distributions. So a discrete random variable, and the binomial distributions is a discrete distributions. So a discrete random variable capital X, okay, is said to have a binomial distributions with parameter p, and p is in the interval 0 to 1, and n is a positive integer. So in that section there are two parameter n and p. N is a positive integer and p is lies in the interval 0 to 1. If its distribution is given by, and this is the distribution function where x is equal to 0, 1, 2 and up to n. So in that case where the sample points are the finite, and the corresponding the probability mass function fi, and it will be f0 corresponding to a 0, f1 corresponding to 1, f2 corresponding to 2 and up to fn corresponding to n. So where the probability mass function fi, and this is equals to probability of x is equal to I, and it is equals to nci p to the power I into 1 minus p whole to the power n minus I, where I is equal to 0, 1, 2 and up to n. So this is called the binomial distribution, that is denoted by fi, or probability of x is equal to I, and is defined as nci p to the power I into 1 minus p whole to the power n minus I. And there are two parameters, and the parameters are p, and p is lies in the interval 0 to 1, and n is a positive integer. Okay, and for instance one probability mass function f1, and this is actually when we put I is equal to 1 in that section, and we will get f1, and f1 is equal to nc1 p to the power 1, that means p into 1 minus p whole to the power 1. So that means np into 1 minus p whole to the power n minus 1. This is the probability mass when we put I is equal to 1. So thus the probability mass function, that is PMF in short, fi satisfied the two fundamental properties of the distribution function. fi is greater or equals to 0, and summation over I is equal to 0 to infinity fi is equal to 1, and which can be easily verified. And I have already mentioned in the previous class, where the probability mass function fi is given, and fi is always greater or equals to 0, and summation over I is equal to 0 to infinity fi is equal to 1. Okay, and then when the random variable capital X has a binomial distribution with parameter n and p, and we can write it as x equivalent to p of n comma p. So any binomial distribution is denoted by p of n comma p, and where n is the positive integer and p is lies in the interval 0 to 1. Okay, so n and p are the parameter of the binomial distributions, and we say x is a binomial variant. And number 3, the significance of the parameters n and p would be given is subsequent theorem. Okay, so there are 3 notes on the binomial distributions. First one are the properties of the binomial distributions. Summation over fi is equals to 1, as well as fi is greater or equals to 0, and any binomial distribution can be written as this: x equivalent to p of n comma p, where n and p are the parameters. Okay, and this one. And after that we will talk about the cases where the binomial distributions are fit. Okay, let A be an event of a random experiment capital E, and we call the event A is a success. Okay, so and A is a subset of sample spaces, and the event not A is equal to say failure. Okay, so in a binomial distribution there are two possibilities. The first possibility is success and second possibility is failure. So here p is equal to success and 1 minus p is a failure. Okay, so let p is equal to probability of success in a single trial of a experiment E, and E be repeated independently n times. Okay, so then capital X is equal to number of success in n trials. So then, so here in a binomial distribution, p is the and n are the parameters. So n is the number of trials, and p is the probability of success in a single trial. So then X may assume the values 0, 1, 2 and up to n. So there in a binomial distribution the number of sample points are the finite, and it is 0, 1, 2 and up to n. And where p is the success and n is the number of tiles, total tiles. So for example, the event x is equal to 3, that means 3 success in n trials, and it can be shown that probability of x is equal to I is equal to NCI p to the power I into 1 minus p whole to the power n minus I. And if we take x is equal to 3 in a binomial distribution, then it will be changed. That means probability of x is equal to 3 is equal to NC 3 p to the power 3 into 1 minus p whole to the power n minus 3. Okay, so thus the distribution function x becomes x such that 0, 1, 2, 3 and up to n, and the corresponding the probability mass function fi, that means f0, f1, f2 and corresponding to 0, 1, 2 and up to fn corresponding to n. So where the probability mass function fi is equal to probability of x is equal to I, where x is the event, and this is equals to NCI p to the power I into 1 minus p whole to the power n minus I, where I is equal to 0, 1, 2 and up to n. So this is called the binomial distributions, okay, and is denoted by fi, or probability of x is equal to I, or p of n comma p, where p and n are the parameters, where p is equal to probability of success in a single trial and n is a number of trials, total trials. Okay, so thus the number of success in n trials in a binomial variate with parameter p is equal to probability of success in a single trial and n is the number of trials. Okay, this is called the binomial distributions, and it can be written as NCI p to the power I into 1 minus p whole to the power n minus I. After that we will talk about some related theorem on binomial distributions. So if the random variable capital X has binomial distributions with parameter n and p. Okay, so here n is the positive integer and p lies in the interval 0 to 1. Then its mean is n into p, that is the expectation is np, and its variance is npq, where q is equal to 1 minus p. So here is the proof of the theorem. Here x is equal to, x is the random variable and x is equal to 1, 2, 3 up to n. Okay, so here x is a discrete random variable in that case. So here its probability mass function is fi, and fi is equal to probability of x is equal to I. In a binomial distribution, it is NCI p to the power I into 1 minus p whole to the power n minus I. So the mean of this distribution, and the definition of mean for the discrete case, it is expectation of x is equal to summation over I is equal to 1 to n I into fi. Okay, so this is equals to summation over I is equal to 1 to n I into NCI, and fi is the probability mass function, and it will be NCI into p to the power I into 1 minus p whole to the power n minus I. So from this we will get summation of I is equal to 1 to n I into NCI p to the power I into n minus p whole to the power n minus I. Okay, and NCI, and it is written as after cancelling the term I, and from this we will get n into p, where p is the parameter. Okay, so it is not a variable, and also n is a parameter. So np into summation over I is equal to 1 to n minus 1 c I minus 1 p to the power I minus 1 into 1 minus p whole to the power n minus I. So now replacing I minus 1 by r, and this summation will get summation over r is equal to n minus 1 cr p to the power r into 1 minus p whole to the power n minus 1 minus r. And this is the binomial distribution of p plus 1 minus p whole to the power 1. The binomial distribution of p plus 1 minus p whole to the power n minus 1, and it is actually summation over r is equal to 0 to n minus 1 into n minus 1 cr p to the power r into 1 minus p whole to the power n minus 1 minus r. Okay, so p plus 1 minus p whole to the power n minus 1, and from this we will get the value 1. So after cancelling the term p, and from this we will get 1. So therefore the expectation or the mean of a binomial distribution, and it will be n into p. And after that we will find the variance of the binomial distributions. And there is a properties of the variance. Variance of x is equal to expectation of x into x minus 1 minus m into m minus 1. This is one of the properties of the variance. Okay, and I have already mentioned in the previous class. Okay, so now expectation of x into x minus 1, and it is equals to summation over I is equal to 0 to n I into I minus 1 into fi, where fi is the probability mass function, and it is equals to nci into p to the power I into 1 minus p whole to the power n minus I. So after putting the value of fi, and it will gives summation over I is equal to 1 to n I into I minus 1 into nci p to the power I into 1 minus p whole to the power n minus I. And after cancelling the term I into I minus 1, and n factor I factorial is equal to I into I minus 1 into I minus 2 factorial. And after cancelling the term I into I minus 1, and then from the following summation, it will give summation over I is equal to 0 to n I into I minus 1 into n minus 1 by I into I minus 1 into n minus 2 by n minus 2 c I minus 2. This is the factorial p to the power I into 1 minus p whole to the power n minus I. Now cancel the term I into I minus 1 from numerator and denominator, and it will give n into n minus 1 into p square summation over I is equal to 2 to n minus 2 c I minus 2 p to the power I minus 2 into 1 minus p whole to the power n minus I. Again we take I minus 2 is equal to r, then the summation will be changed, and it will be n into n minus 1 into p square summation over r is equal to 0 to n minus 2 n minus 2 cr p to the power r into 1 minus p whole to the power n minus 2 minus r. And this is the binomial distributions of p plus 1 minus p whole to the power n minus 2. So the binomial expansion of p plus 1 minus p, and it will give whole to the power n minus 2, and it will give summation over r is equal to 0 to n minus 2 cr p to the power r into 1 minus p whole to the power n minus 2 minus r. Okay, and p plus 1 minus p, and it will give 1 after considering the term p, and it will give 1 to the power n minus 2, and it will, that means 1. So therefore expectation of x into x minus 1, and it will give n into n minus 1 into p square. So therefore the variance of x is equal to expectation of x into x minus 1 minus m into m minus 1, where m is the expectation or expected value of the binomial distribution. And this is the properties of the binomial distributions, for the discrete case. So therefore here m is equal to, I have already found this one, m is equal to n into p. So now putting the value of expectation of x into x minus 1 as well m, that means the mean of the distribution, and it will give n into n minus 1 into p square minus np into np minus 1. And from this we will get np into 1 minus p. and you know 1 minus p is equal to q. So the variance of the binomial distribution, and it will give n into pq. Okay, so here q is equal to 1 minus p, and as well the standard deviation sigma, and it will give root over of variance, you know, positive root of variance, that means root over of n p q. Okay, so this is the most important theorem on the binomial distributions. So in a binomial distribution, the expected value is n into p, where n and p are the parameter, and n is the number of tiles, that means n is positive integer, and p is the success, that is p is lies in the interval 0 to 1. This is the probability value, that is probability of a success, that means it is lies in the interval 0 to 1. Now we are going to take some examples on the binomial distributions. So the first example, it will be the mean and the standard deviation of a binomial distributions are 4 and root over of 8 by 3. Find the value of n and p, and hence evaluate probability of x is equal to 0. So here is the solution of the given problem. So we know the mean and the standard deviation of the binomial variate are respectively np and root over of np into 1 minus p, or np into q, where q is equal to 1 minus p. And therefore, according to the question, np is equal to, so np is equal to mean, and np is equal to 4, and the standard deviation, you know, root over of 8 by 3, so variance is equal to root over of 2 whole square, that means 8 by 3. So therefore np into 1 minus p, and it will give 8 by 3. Okay, so now from these two equation, and we'll get the value of p, and you know the value of p is equal to 1 by 3 after calculating or eliminating n from these two, we'll get the value of p. So p is equal to 1/3. And from the first equation, we will get the value of n, and n is equal to 4 into 3, that is here p is equal to 1/3. So n into p is equal to 4 into 3. Okay, that means 12. So therefore the parameter n is equal to, n is the number of tiles, and it is equals to 12, and the probability of success p is equal to 1/3. Okay, so after that we are going to find the probability value of x is equal to 0 in a binomial distribution. So you know, in a binomial distribution, probability of x is equal to 0, and it is equals to f0. That means 12c0 p to the power 0 into 1 minus p whole to the power 12 minus 0. Okay, so you know 12c0 is equal to 1, 1/3 whole to the power 0 is equal to 1, and 1 minus 2 by 3 whole to the power 12 is equal to 2 by 3 whole to the power 12. So therefore the probability of x is equal to 0 in a binomial distribution, and it will give 2 by 3 whole to the power 12. Okay, so after that we will talk about the some more examples on the binomial distributions. So here we will take examples. The example 2 on binomial distributions. The mean of a binomial distribution is 3, and the variance is 3 by 2. Find the probability of obtaining at least 3 successes. This is the problem. So here the mean of a binomial distribution, that means np is equal to 3, and variance, that is np into 1 minus p is equal to 3 by 2. And from this we will find the probability of obtaining at most 3 successes. That means probability of x lesser or equal to 3. Okay, so here capital X be the random variables corresponding to the number of success, then their probability mass function of x is, you know, fi is equal to, in a binomial distribution, fi is equal to probability of x is equal to I, and this is equals to nci into p to the power I into 1 minus p whole to the power n minus I, and where I is equals to 0, 1, 2 and up to n. So according to the question, where mean is equal to 3, that means np is equal to 3, and the variance, that means np into 1 minus p is equal to 3 by 2. Now divided by np is equal to 3 on the second equation, then from this we will get 1 minus p is equal to 3 by 2 by 3, that means p is equal to 1 by 2. And putting the value of p in the first one equation, it will give n, and n is equal to 6. So number of tiles in a binomial distribution is equal to 6, and success of a binomial distribution, that means the probability of success of a binomial distribution is 1 by 2. Okay, and applying this these two parameter, we will get the probability of at most 3 success, and it is equals to probability of x less or equal to 3. So from this we will get probability of x is equal to 0 plus probability of x is equal to 1 plus probability of x is equal to 2 plus probability of x is equal to 3, and this is equals to probability of x less or equal to 3. Okay, so in a binomial distribution, probability of x is equal to 0, that means 6 is 0, 1 by 2, so here p is equal to 1 by 2, so 1 by 2 whole to the power 0 into 1 minus 1 by 2 whole to the power 6. And at probability of x is equal to 1, the binomial distribution, it will be 6c1 1 by 2 whole to the power 1 into 1 minus 1 by 2 whole to the power 6 minus 1, that means 5. And when x is equal to 2, so the binomial distribution at that point is 6c2 1 by 2 whole to the power 2 into 1 minus 1 by 2 whole to the power 6 minus 2, that means 4. And the last one, that is probability of x is equal to 3 in a binomial distribution, it will be 6c3, this is actually 3, 1 by 2 whole to the power 3 into 1 minus 1 by 2 whole to the power 3. And after calculating this 4 terms, and from this we will get the value of the probability, will get the probability value of at most 3 success, and it will be 21 by 32. Okay, let us move on the next slide. So in this slide we will take the another examples on the binomial distributions. The probability that a pen manufactured by a company will be defective, 1 by 10. Okay, so if the company manufacture 10 pen, and among this 1 pen is defective, so if 12 such pen are manufactured, find the probability that exactly 2 will be defective, none will be defective, at least 2 will be defective. Okay, so there are 3 parts of this problem. So first part, it will be, we will find the exactly 2 will be the defective pen, none will be the defective pen, and third one is at least 2 will be the defective. Okay, so here the company will defective where the company manufactured by where the pen manufactured by the company will be defective, 1 by 10. Okay, so here is the solution. Let defective pen is equal to success. So probability of success of a single trial, and it is equals to say p, and p is equal to 1 by 10, and the experiment is repeated 12 times. Okay, so that means n is equal to 12 in that case, and n is the number of trials, and p is the probability of success. So let the random variable capital X is the number of defective pens. So then x is a binomial variate where the parameters are n is equal to 12 as well as p is equal to 10, 1 by 10. Okay, so where p is the probability of success and n is the total number of trials. So its probability mass function is fi is equal to probability of x is equal to I in a binomial distribution, and it will be 12ci 1 by 10 whole to the power I into 1 minus 1 by 10 whole to the power 12 minus I. Okay, so this is the binomial distribution where the probability of success is equal to 1 by 10, and the total trials, that is the number of trials, is 12. and probability of success, it will be the number of defective pens. And from this we'll get the answer of the following three questions. And the first problem, it will be exactly 2 will be the defective pens. So that means the required probability is the probability of x is equal to 2. So here x is the number of defective pens. Okay, so probability of x is equal to 2 in a binomial distribution, it will be 12c2 1 by 10 whole to the power 2 into 1 minus 1 by 10 whole to the power 10, that means 12 minus 2, that is 10. So after calculation, it will be 66 into 10, 9 to the power 10 by 10 to the power 12, and from this we will get 0.2301. Okay, so this is actually the required probability of exactly 2 defective pen. And after that we will find the probability value of no defective pen. That means probability of x is equal to 0. And from the binomial distribution, it will give 12c0 p to the power 0, that means 1 by 10 to the power 0, 1 minus p, that means 1 minus 1 by 10 whole to the power 12 minus 0, that is 12. And after simplifying this one, and that means 12c0 is equal to 1 by 10 whole to the power 0 is 1, and 1 minus 1 by 10 whole to the power 12 is equal to 9 by 10 whole to the power 12. And from this we'll get 0.2833. Okay, this is the required probability of none of the pens are defective. And after that we will find the probability value, that means probability of x greater or equals to 2. That means the at least 2 pens are defective, and the required probability is probability of x greater or equals to 2. That means 1 minus probability of x less than 2. And probability of x is equal to 1, it will be 12c1 into p to the power 1 into 1 minus p whole to the power 12 minus 1, that means 11. And from this we will get the value of probability x is equal to 1. That means one ball is defective, and it will be 12 into 9 to the power 11 by 10 to the power 12. That means 0.3755. This is the value of the probability of x is equal to 1. So the required probability, and it will be probability of x greater or equals to 2. So at least 2 pen are defective. So this is equals to 1 minus probability of x less than 2. This is the properties of the probability. Okay. And probability of x less than 2, it will give probability of x is equal to 0 plus probability of x is equal to 1. So here probability of x is equal to 0 is equal to 0.2833, and probability of x is equal to 1 is equal to I have already found this one, 0.3755. And after putting the value of probability of x is equal to 0 as well as probability of x is equal to 1, and from this we'll get 0.3412. This is the probability value, or the required probability of at least 2 pens are defective. Understood? So after that we will take one more example on the binomial distributions. So here is the problem. A defective die is thrown 10 times independently. Then the probability that an even number will appear 5 times is twice the probability that an even number will appear 4 times. What is the probability that odd face appear in each of the 10 throws? So here is the solution of this given problem. So let even face is the success. So x is equal to number of even face among 10 tiles. So n is the number of tiles and n is equal to 10. Okay. And x has binomial distribution with parameter n is equal to 10 and p. And p is unknown in that case. Okay. And according to the question, we will find the value of p. So the probability mass function is given by fi is equal to, in a binomial distribution, fi is equal to probability of x is equal to I, and this is equals to 10 ci into p to the power I into 1 minus p whole to the power 10 minus I. So by the problem, probability of x is equal to 5 and this is equal to 2 into probability of x is equal to 4 according to a question. So probability, the probability that an even number will appear 5 times is twice the probability that an even number will appear 4 times. So according to the problem, it will give probability of x is equal to 5 is equal to 2 into probability of x is equal to 4. Now applying the binomial distribution on both cases, we'll get 10c5 p to the power 5 into 1 minus p whole to the power 10 minus 5 is equal to 2 into, and probability of x is equal to 4, this is equals to 10c4 p to the power 4 into 1 minus p whole to the power 10 minus 4. And after simplifying this, we'll get 10c5 into p is equal to 2 into 10c4 into 1 minus p. And from this we'll get the value of p. That means 252p is equal to 2 into 210 into 1 minus p. And from this we'll get the value of p and it will be 5 by 8. Okay. So the required probability, that means we are going to find the probability that the odd faces in each of the 10 rows. So odd face is not appear in that case. So that is, we are going to find the probability of x is equal to 0. And this is equal to 10c0 p to the power 0 into 1 minus p whole to the power 10 minus 0. Where n is the number of trials and p is the number of success. So in that case, where number of success is 5 by 8, I have already found this one. So from this we'll get 1 minus 5 by 8 whole to the power 10, that means 3 by 8 whole to the power 10. This is the required probability. That means the odd faces will appear in a binomial distribution and it will be 3 by 8 whole to the power 10. Okay. So after that we'll take the fifth example, and this one is actually if x be a binomial distribution with the expectation value is 2 and the variance is equal to 4 by 3. And from this find the distribution function of x. So in that case, where the distribution function is the discrete distribution, So here is the solution of the given problem. So here we have expectation of x is equal to 2 and variance of x is equal to 4 by 3. And the expectation of a binomial distribution is np and variance is np into 1 minus p. So np is equal to 2 according to the question, and np into 1 minus p is equal to 4 by 3. And after solving these two equations, we'll get the two unknown values, that is n and p. So here p is equal to 1/3 and n is equal to 6. So n is the number of trials in a binomial distribution and p is the probability of success, So therefore q is equal to 1 minus 1 by 3, that means 2 by 3. Okay. So q is the failure or the probability of failure of a single trial. So therefore probability, so from this we are going to find the distribution function, So in that case, where the total number of trials is 6, okay, and the success is 1/3. So here f0 is equal to probability of x is equal to 0. That means in a binomial distribution 6c0 1/3 whole to the power 0 into 1 minus 1 by 3 whole to the power 6 minus 0. And from this we'll get the value of the probability x is equal to 0. That means 64 by 729. And after that we will find the probability mass function, that means f1, and it will be probability of x is equal to 1. So in a binomial distribution it will be 61 1/3 whole to the power 1 into 1 minus 1/3 whole to the power 6 minus 1, and it will give 64 by 249 after simplifying this. Similarly, we will find the probability mass function f2 is equal to probability of x is equal to 2, and this is equal to 62 1/3 whole to the power 2 into 1 minus 1/3 whole to the power 6 minus 2, and after simplifying this it will get 80 by 243. Okay. So similarly we will find f3, f4, f5 as well as f6. So there are 7 spectrums, so 0 1 2 3 4 5 6. So f3 is equal to after calculation we'll get 160 by 729, F4 is equal to 20 by 243, F5 is equal to 4 by 243, and F6 is equal to 1 by 729. After calculation, we get these values. Therefore, the required distribution function of x is 0 at a point 0, Fi is 64 by 729. At x is equal to 1, it will be 64 by 249. At x is equal to 2, it will be 80 by 243. At x is equal to 3, it will be 160 by 729. At x is equal to 4, it will be 20 by 243. At x is equal to 5, it will be 4 by 243, and the last one, x is equal to 6, it will be 1 by 729. And this is the required distribution function of the following problem. Okay, so after that we will take another example of a binomial distribution. So the probability of man hitting a target is 1/3. So that is the success is 1/3. Okay, if he fires 5 times, what is the probability of hitting the target at least twice? And the second probability will be how many times must he fire so that the probability of his hitting the target at least one is more than 90%. So here is the solution of the given problem. So here P is equal to probability of hitting, and this is equal to 1/3 according to the question. And you know Q is equal to probability of no hit, that means 1 minus 1/3, that is 2 by 3. Okay, and in the first problem it will be if he fires 5 times, so what is the probability? So we are going to find the probability of hitting the target at least twice. So here n is equal to, n is the number of tries, it is 5. Then and x is the the number of hits in a single trial. So therefore probability of x is greater or equals to 2. So we are going to find this probability value, that means x greater or equals to 2. And this is equals to 1 minus probability of x less than 2. And from the properties of a probability theory, you will get probability of x greater or equals to 2 is equal to 1 minus probability of x less than 2. And from this we will get 1 minus probability of x is equal to 0 minus probability of x is equal to 1. So at probability of x is equal to 0, the distribution function, that means the binomial distribution, it will be 5c0, 1/3 is the p, so 1/3 whole to the power 0 into 1 minus 1/3 whole to the power 5 minus 0, as well as at x is equal to 1, it will be 5c1, 1/3 whole to the power 1 into 1 minus 1/3 whole to the power 5 minus 1. And after simplifying this, it will give 1 minus 5c0, 2 by 3 whole to the power 5 minus 5c1, 1/3 whole to the power 1 into 2/3 whole to the power 4. And after calculating this equation, that means the above equation, we will get the value, and it is 131 by 243. And after that we are looking for the second part of this problem. So let n be the smallest number of fires so that the probability of hitting the target of least once is more than 90%. So by the conditions, probability of x greater or equals to 1, and this is greater than 90 by 100, that means the 90%. And there is a properties of the probability function. The probability of x greater or equals to 1, it is equals to 1 minus probability of x is equal to 0. Okay, and this is also greater than 0.9, that means 90 by 100, it will be 0.9. And probability of x is equal to 0, that will give 2 by 3 whole to the power n. So 1 minus 2 by 3 whole to the power n, and it is greater than 0.9. And from this equation we will see that 2 by 3 whole to the power n is less than 0.1. Now taking log on both sides, we will get n into log of 2 by 3 is less than log of 0.1. So log function is the increasing function. After taking log, we will get this one. Okay, so here the inequality is not changed for the increasing function. So n into, and from this we will get n into log of 2 by 3 less than log of 0.1. So therefore n greater than log of 0.1 by log of 2 by 3. So that means n greater than 5.679. So after putting the value of log 0.1 and log 2 by 3. So n is approximate equals to 6. Thus he must fire 6 times. This is the solution of the second part of this problem. Okay, so I'll stop here. Thank you.